Okay, hello everyone. Just give me about 5 seconds to get set up. I'm always super confused when I start these up. Okay, this is there. Should be good, I guess. Conversion strategies at scale. Okay. Hey Camille, how are you? Okay, good. Perfect. Hello everyone, how are you? I hope everybody is doing okay. So okay, we're good. So today we're gonna review a pretty nice paper. I've been reading it the whole week. Kind of paper that that's it, like a kind of the method that haven't encountered much. Evolutionary strategies. If you think about it, it's mostly it's like a superset of the biologically related method with evolution, all this stuff with mutation and whatnot. In this specific case, it's applied to like fine-tuning LLM, which is really weird. None of it should technically work, but it do work even better than RL, at least on their specific task that these guys have been working on. Yeah, wait a second. Oh geez. Yeah, these guys that have been working on. So that's what we're gonna look at today. I just got an issue with my shit. My board is messed up. Is it AWS again? Oh geez. Oh no, I've been preparing the whole thing. Give me a second here. No, I think this one we're gonna have to take a look straight at the paper. Okay, so overall result, we're gonna be able to take a look at it there. I prepared the whole board, but it seems like I hadn't saved at all. So now you guys can't see anything. This is these results here. Yeah, I just need like 2 minutes. I'm gonna like bring them back here. So that's one thing over there, and then I can take that from the appendix. So overall, great technique. It was pretty cool to see in action. But it does look a bit weird, right? That it actually just work. Like these techniques usually are used in like very small scales, and yeah, not at all at like LLM level, right? That's what's happening here. And a cool thing is we're gonna actually have one of the researchers. I managed to get him into an interview for later this week. So we'll be able to ask him all of our questions, right? On is this real, right? Like, is this, are we actually seeing something that is real? There's a few things that in the paper that are, I would say that like are a bit counterintuitive. Is that like they are mostly using two benchmarks that are good for like longer kind of RL kind of task. The countdown task, and then another one that is like for conciseness. This is more for reward hacking, but it's interesting that like they haven't used the kind of normal RL benchmark in this case. Yeah, so okay, I got this there. My quick visualization here. I just need to pull out the GRPO and PPO, and then I think we're in business. Yes, this one can dump it there. Boom. Okay. And oh yeah, I also need the related work. Okay. This one, this one, this one, and this one. Yes, another one from Uber, and then another one from this. Okay, not too bad. I think we're good, right? Lab algorithm. Second one. Okay, sorry for that. My Tildra hasn't saved really well. Okay, perfect. So, hi Santi, hi Yuli, hi Ali. Hope you guys having a great day. So the paper, I actually haven't give you the link, but it's this one. Evolutionary strategy for LLM fine-tuning. Fine-tuning beyond reinforcement learning, exactly this one. So you can check it here and follow along if you want to, right? Pretty concise, honestly. It's not too bad of a paper. I think I would have liked a bit more kind of benchmarked in this one, but overall pretty good, pretty thorough. The methodology is kind of suspiciously how to say it, like suspiciously simple, right? Like if you look at the method for the algorithm, it's just this. We're gonna go through it, but like you're basically just wiggling a bit the parameter space. Anyway, so this is this. So the paper is that the two main thing that is important is like this is the kind of method that was kind of killed off because of theoretical foundation that it shouldn't work, right? Which is always kind of interesting to see, because like it happened in the past that like this shouldn't work, and then like we actually tested, and for a weird reason it actually do work. So everything is fine, we can actually use it, and it has some great properties, right? So this is the case. I'll show you the paper that actually killed that, and the exact section that it kills it is like in the discussion that says like it shouldn't kill when like the parameter space goes big, and LMs have big parameter space, so people were like shouldn't work. There's a few things that these guys are doing that are very peculiar compared to the literature, which might explain why like this is happening in the first place. So the kicker for this is the following. They have a full parameters of LM, so they think they go from 0.5 to like 8 billion parameters, and evaluation strategy can search efficiently over billions of parameters and outperform existing RL fine-tuning method in multiple respects, including sample efficiency, which is weird, right? Sample efficiency, I would have thought that like is like RL will be much more sample efficient. Actually, no. In this case, ES is more sample efficient. It is better at long horizon reward task compared to RL, which like struggle when like there's multiple reward. But like you have to take everything with like an asterisk here. There's just like one task that they're doing, right? And it's the countdown task. Robustness to different base LM. This is very true because like they don't have like they're not doing hyperparameter tuning. They're doing one set of parameter for ES over the every network, every task, right? So just one set. And RL, they're fine tuning it, like fine tuning the parameters. they have less tendency to reward hacking. They have one benchmark that shows this, so the conciseness task, and more stable performance across run. The gist of why this happening is that like ES is learning a distribution, while RL is trying to find a solution, right? So it has a distribution of solution versus like one solution. Hey Adil. So that's the gist of it. The algorithm is this one, like I showed you, right? If you look at it, it's like it's 2 for loops, and it, like here we're just like look, we're just wiggling a bit the parameter space, and then like we get a bunch of rewards, and then we use that to like update the model parameters. But effectively, we're just like randomly jiggling it. But all of this has to happen with verifiable reward, right? Because like that's kind of how what we have. And then you see these results. It's kind of, I think it's crazy, right? Look at it. Like it also works with small model size. So you see here we have 0.5, like PPO, GRPO, it kind of like not work that much, right? In terms of performance. This one like 14% improvement, right? Across the board. And like look at this, like the 3 and 7B, it's like it's pretty good. It's like 10% and more than GRPO. Yeah, it's pretty good. Like I don't know what to say. It's like it actually seems to be working. And the code is open. Also, you can check it out and run it for yourself. I know somebody was running it and had some issues, so you can check it out. The code is actually right. It's right over here. It's first page actually. Right, and it's not like some crazy code, like it's just this. It's this one, so with the independent direction, yeah man, it's like it's a few lines of code, 400 roughly, right? You can check it out over there in the paper and test it out for yourself. There is some like improvement that they did in like the base algorithm that I'm going to show you in order to make it GPU friendly and work across different GPUs. So that's pretty much it. Remember, the purpose of this kind of space is for you to ask a whole bunch of questions. So if you have questions that is not related to this, it's the perfect setup to do so, because that's the point, right? The point is for you to air out all your dumb questions to me. I'll answer anything. I don't mind. Yeah, and I'll take pause from time to time to answer them. Yeah, overall, I would say, right before we go into it, actually a good paper. And I think like, I don't know, like if they manage to showcase more, I don't know, like more hint that this can actually be very good for like across LLM family, bigger and bigger parameter size. What are the drawback also? Because there was no drawback at all in all of this paper. It was like, it's fantastic, it fucking worked. So like some of the drawback also, if they can area out in like a future work, it would be nice. If you have any question also for the guy that we're gonna interview on Thursday, just drop them there. I'll just like compile them so that we can have them for Thursday. And yeah, I think like if this actually seems to be very good, it can become like a, not a default, but like a good fine-tuning method, right, for LLMs. So before we go on, let's thanks to sponsors, right, like always, because this is now a big boy live stream. First sponsor I would like to thank is actually you guys. Thank you very much, right? A lot of you have been subscribing to this channel, but not like as a subscriber, but like more of like as a member. I have a few tiers, so I have like this like 90 cents tier and this $10 per month tier. You get access at $10 like to like some archive live stream that I'm doing. So after a while, I just take them and like I put them into kind of an archive, so you get access to this. But I always super like to see all of you guys, because I recognize some of you from Twitter, right? You're all a bunch of researchers and stuff. Like, look at this dude, Michael. You're like in a poster session. I just find it really cool that you guys are supporting the channel. So like big thanks to you. So this is these guys, and then also Scrimba, which is actually literally sponsoring some of these live stream. So big thanks to you, Scrimba. And if you don't know, like I've been like talking about this, Scrimba is like kind of an education platform, right? And it's kind of was made for the front end people back in the days, but now like they have like a full stack kind of developer path. So like that's it. I get a lot of questions about like what you should learn in terms of like to be kind of get a job in AI, like machine learning. I think one thing that you have to remember is that now, like the swing of AI is overly indexed on the engineering side, right? So like having good engineering skills in general is pretty useful, right? So like DevOps skills, backend skills to like duct tape your stuff, even like API, like duct tape type of skills, super useful. They have like a full stack developer path, right? 100 hours, totally crazy. And the one part that is interesting is this part for you. So the AI engineering kind of course, because like what's interesting about the AI engineering one is that like they actually literally show you how to build a bunch of apps, right? So it's like kind of toy apps for some that you can take up and then like improve if you want. But it shows you the rough skills that you actually need to make like good AI workflows, right? Some of them you're gonna deal with agent. Some of them you're gonna deal with like fine tuning. You have a whole RAG setup, right? And then they show you where you have to go to kind of learn and dive a deep more. One thing I like is that like the actual UI, I don't know, man, like the actual UI is pretty cool. So you have the video that is running, right? So the video is running and blah, blah. It's gonna teach you a bunch of stuff. You have the deck over here. But the important point is that at any point you can stop and actually like, it's an IDE, right? So you can go and play and change the code, and then there's some challenges that you have to do. And you can save the code, you can go over here, right? And then like just like literally download the code as zips. And then like you have it into your own environment and stuff like that. So I really feel like it's a great platform if you want to actually go and then do your learning in a more hands-on way. So that being said, thank you guys, and thank you Scrimba for sponsoring this stuff. So before we start, you can take a sip. Okay. Don't hesitate if you have questions as we go. So if we look at the overall result, we're gonna start here and dive a bit deeper on it. It's absolutely bonkers, right? The actual task, am I gonna show it to you right here? The actual task is this one, right? So it's actually this. So you have, let's say, a bunch of iterations, and this is your input, right? You're a helpful assistant. You first think about the reasoning process in your mind and then provide the user with the answer. So you have a bunch of numbers, right? So like these numbers, and then you have a bunch of operation. So these operation, right? And then you have to kind of like combine them together in order to get like a final number, in this case 44, right? So that's kind of what you give to the model. And then like there's two ways we're gonna like improve the model. We're gonna fine tune it with RL, or we're gonna do like a evolutionary strategy. And then the response will look like this. So you have like first is considered like the normal reasoning type of stuff, right? That is running. It will go like this, and then at the end it will like give you like the actual final answer, which is that, right? So it shows the reasoning that you have to do in order to get to 44 in this specific case. Yeah, so that's kind of what we're looking at here. That's like one of the only benchmark that they have in this paper. So in this, when we're benchmarking PPO and then GRPO with like eight groups, and then GRPO with like 30 members here in the group, and then this is their thing, right? So if you see, we have two family. We have the Quen family and the Llama. I think I have a third one. No, actually, they just have two. So Llama from 1 to 8, and then Quen from 0.5 to 7. Generally, like the smaller model, when you're trying to fine tune them with RL, it kind of doesn't work, right? There's ways to make them work, but even with the R1 paper back in the early January, it was not working, right? So you have to do a whole bunch of tricks in order to make it work. In this case, none of them are able to do it, but like ES is actually able to do it on these small model. So this is surprising, and like the performance is just like better all across, right? It's tighter here, let's say, in the 1B for Llama over here, but other than that, it's always like 10% above RL. Which is wild. And then like here, look, the same hyperparameter we use for all ES run. So they're using like one set of hyperparameters, and then they just run this like through the whole thing. And versus like GRPO and then PPO, they actually have a grid search going on for like their different parameter. Yeah, so that you can see it in the appendix. So if you look at here, like in bar chart, look at it, there's a lot of I don't know, there seems to be a lot of gap, right? And like here, see this 0.5B, it's massive, like crazy. So like that's the gist of it, right? And yeah, we're gonna take a look at the method in more depth now. But overall, what's happening is the following over here, right? So you have your model policy, right, in the middle. So this is like in parameter space, let's say you have 2 parameter, right? And then you have like all of the point is like the little change that they're doing in the parameters to where it should be, right? And then they're gonna evaluate like the model performance, because there's a reward function at the end of this, right? To see, is this a good spot to be, right? And then basically what you're gonna do is you're gonna average out the direction, right? You're gonna take all of this information and you're gonna average them out, and then you're gonna go toward this like averaged out direction over a population. In this specific case, we're doing 30 of them. So you're like running 30 of these model in parallel, and then you're gonna just like have the reward for these 30 directions. So let's say right now the reward is bland. Everywhere the reward is like garbage. But let's say we want the model to go like over here, right? You want it to go over here. You see, if we give it a bit of reward here, it would just go and then like go and then like iterate, and then it will land in the middle of it, and then that's that, right? And it works for multiple shape, right? And this is in two dimension, but you can imagine this happening like at multiple dimension. It's the same idea, right? And each of the parameters are kind of independent in this case. Like they're gonna wiggle each of the you're gonna add noise for the wiggle in each of the parameters a bit like differently, and there's gonna be a sliding variation of noise that you're gonna add, and it's just like a stochastic process literally, right? So you have the full model that is already pre-trained, right? And then you're just wiggling a bit the parameter, and then calculating a bunch of reward, 30 of them per run. And then you look at where it's the best direction, and you just kind of go there. It's the gist of the it's the gist of the thing. They have also another visualization, I think on the repo, but it's the same idea, right? So like this is based on this countdown task like that they have, and it's just gonna go where like where it's better. If we look at this compared to the rest, PPO, there's actually a value model in it, right? There's a value model in the stuff. So you have your trained policy model, and then you have the value model, and your policy model is the LLM that you're trying to fine tune, okay? And then this will generate like the V, which at the end of the day will generate your advantage, right? And the advantage is what you're gonna use over there. And then the value model, the issue is that you have to train it on top of like whatever you're doing on the rest. So like that's the one thing. GRPO kind of simplify that. So now GRPO is like what's mainly used. Depending, like for LLM, this is GRPO that is mainly used. In other setup, PPO is still a very good algorithm to use. So the GRPO, what happen is that the reward and reference model, the value model is your reward model. There's no difference, right? You're just doing multiple sampling of the multiple sampling of the output. So instead of doing just one output, you do like, I don't know, 30 output. This is your group, right? And you give that to the reference model, the reference model and the reward model, And then with the weird model, you're gonna get a bunch of reward. You're gonna average them out, and then like you're gonna be able to get like all these advantage, which will be used in a specific formula to update the policy, right? It's kind of doing the same thing as this. If you think about it, right, you can look at the same kind of stuff, right? But you have like multiple direction that you're sampling from, and then with these direction, you're gonna go there. The difference here is that these direction are made by wiggling the parameter space, right? In this case, it's not wiggling the parameter space at all. Like the parameter space stays constant, it's doing multiple output of the same parameter space. And then like the reward will tell you if like what you did was kind of good or not, and on each of the token, whatever it is. In this case, it's different. It's like, you're wiggling the parameter space, and the output will be whatever the output is. It doesn't matter. Even if the output is like 100 of lines long and you just keep on going, it's just fine, right? It's not on the action space that you're running. It's on the parameter space. And then like the whatever reward that you did, right? Whatever happened will like dictate how your direction that you should change the parameter, because you actually literally already changed the parameters, right? And that's it. And then like the actual formula is very simple. You have your reward over here. You have the degrees of which like you change the parameters, and then you have like an average, right, that you run on all of these different directions. And that's it. And then you have learning rate, and you just update the parameters, right? Where it becomes tricky, right, is like how to do that efficiently, because that was one thing that was always in the literature, is like, this will never work because like the parameter space explode and like it's gonna be garbage to do it. They find ways of keeping the algorithm super simple and then doing it efficiently at kind of a good scale, right? And it's GPU friendly, right? It's very GPU friendly how they did it. They have like 8 different updates that they did on the base algorithm. Yeah, and now like they're able to run this on GPUs, and it's pretty good. You have to do the change in parameter space, like the wiggling, smartly, and then you have to make sure that like the memory is well used, right? Because like Finetuning is usually like memory bound than anything else, right? So if you can save your memory as much as possible, then you can have a better performance. So that's kind of the idea. Any questions so far? We're doing a whole bunch of wiggling. Okay, so let me show you a bit the first base algorithm, right? So here's what you have. You have your pre-trained LLM, right? And this is the initial parameter, and then you have a reward function. So like this is like a verifiable reward type of stuff that we're doing. You have the total iteration that you want to run this. And then you have the population size, which is like how many of these different model you want to spawn around your thing. And then like, yeah, so in this case it's 30. In other literature, it was 10,000, right? This is one of the reasons why they say it couldn't scale. And then you have the noise scale and the learning rate. So these are the two kind of input parameters that you have. So you're iterating, right, over 10, like whatever iteration that you want, and then like this is where you're gonna create like your n number of model, right? And then you're gonna sample some noise, right? The noise over here from a normal distribution, and then you're gonna compute the reward for the perturbed parameters. It looks simple, right? But most of the engineering is actually on this, right? On this part over here. And what happened is that you're gonna like propagate the reward like step by step across each of the layer, right? And you're not gonna save much. You're not gonna save the whole model and whatever. You're just gonna like calculate the reward, because like these models are made to be thrown away roughly, right? Because you're gonna calculate anyway like a change with the average reward on all this direction, and it's that change that will then apply in the iteration, right? So basically, it's like all of the parameters, we're gonna do like the noise scales that we've decided here with our sampling of the noise that we've decided over here, right? And that's kind of that. We're doing this, and then we get all of our stuff, right? We get a new model, and then you're gonna have the output. So the rollout that it done, at some point it will output like a number or something like that, like here, right? It will output something like this, right? Here's the answer, and then you're gonna have your function define if this score this thing basically. So you still need to have like good reward function here, and you're gonna accumulate n of these rewards, so 30 in this case, right? And then once you're done, you're gonna normalize them, so just so that like for each of the direction it's kind of the same, and then you're gonna update the model parameter using like an average, right, of like these reward scaled by the amount of noise that you gave to it, right? So if you had a lot of noise in direction, like you're gonna scale by it, and that's it. And then this will kind of average out the proper direction. It's kind of like you're creating this probability distribution. It's not this, no, sorry. It's this distribution of potential robustness of solution in a specific direction. And if this is good enough, this is where you're gonna go. So you're always kind of moving a bit over here. And then you update the model parameter, and this model will be then used into the next section. Here, these 30 that you're running can all run on separate GPUs. And this is what they show, is that you can like literally spawn 31 different process, right? Have them go through the stuff, be very memory efficient, aggregate the whole thing, and then like be able to get like this normalized the normalized reward at the end, and then run with it. So this is the naive algorithm. The GPU friendly one is a bit bigger, but like that's kind of the idea. We have Huli with the unrelated question. Love those. Are you familiar with Stephen Barnes? If so, do you have any opinion about his neuroscience model and how we connect to it to alignment? I think this rings a bell. Stephen Barnes. Oh, it's a guy from Less Wrong, right? The particular focus on the brain algorithm. Now, actually, I don't know his stuff at all. Actually, I know nothing about his stuff. So if you have more information, you can like give me the TLDR. Yeah, to be honest, I guess for background, I have a background in neuroscience, so computational neuroscience. I like this stuff. I like neuroscience. I like AI. I kind of don't engage much with like the overall consciousness discourse with LLMs, and if like they're conscious or whatever. I'm more of a pragmatic AI dude that really like to take stuff from the brain and then try to see if we can apply them algorithmically to AI. Yeah, so it's kind of a bit boring answer, but like it's hard to apply stuff. If you dive deep enough into the brain, it's kind of hard to dive to apply the same kind of ideas in terms of like same labels and stuff to AI systems, because they're just so different, right? It's really not the same. And I think Carpati said it best, like they're kind of alien, right? In a sense, not like they're super smart and whatever, like it's just way different, right? Like it's really not the same kind of vibe you get from them. Okay, so this is good. Before we go there, right? Kind of forgot to put it there, but like we're gonna check out just like 4 papers, right, that are kind of related. So there's this paper from 2017 from OpenAI themselves, right, with Ilya, my boy over there, right? And I like it because it has the same name, right? Evolutionary strategy as a scalable alternative to reinforcement learning. It's the same thing. Evolutionary at scale, LLM fine-tuning beyond reinforcement learning. There's a lot of similarities, but because basically what Ilya said here is that look at this, man. They're running stuff on CPUs. Crazy, man, how things change in less than 10 years. Basically what they're saying is that it actually worked really well, right? And in their case, they were using like that for, you remember when they were doing Atari stuff and like they had this gym thing for RL, and then they were doing StarCraft shit. Like that's kind of where it was used for, like all these stuff, Mujoco, and then like Atari. thing, and it actually is good. It's scaling. You can possible to scale to over 1,000 parallel workers. You can solve 3D humanoid walking in 10 minutes and obtain competitive result on most Atari game after 1 hour of training. It's just good. Like it actually is a good simple algorithm here. So they were saying it was good here, right? What happened is that Uber came in and said also it's actually fucking good, and it's not the same as finite difference approximation. Not finite difference approximation is that you have like the different the actual loss landscape and whatever, and then you're taking 2 points, and then you can kind of estimate a gradient ish, right, like that. It's not really doing this. It's doing something else. It actually is doing something akin to that, but in the on the parameter space, right? And what they said, I think at the end that was interesting. You can read this. This is more like a robotic type of stuff. They said the following: when this is above some threshold, it is not accurate to interpret ES as merely an approximation of stochastic gradient descent, nor as traditional FD-based approximator. Rather, it become a gradient approximator coupled with a compass that seek area of the search space that is robust to parameter perturbation. Because remember, it's actually doing this. It's like doing parameter perturbation, right? And then taking the best reward and like kind of going into that area. So like as you go there, you're most likely to get out, right? Of there. And it's less random than you think, because like one thing that they're saying in this paper that we're reading right now is that like there's actually a low dimensionality to LLMs. That's what they're saying, right, in the parameter space. So they had this, but then you had this this paper actually. So contrasting exploration in parameter and action space, a zeroth order optimization perspective. And what they said here is that like it's great, right? It's a great method. But then they did simple theoretical analysis and we proved that complexity of exploration in parameter space depend on the dimensionality of the parameter space, while complexity of exploration in action space depend on both the dimensionality of action space and horizon length. So like this is very important because it kind of killed the vibe, right? If you look at the discussion here, they said this here. For domain where the action space dimensionality and horizontal length are small and the dimensionality of the parameter space is large, we conclude that exploration in action space should be preferred. So RL should be preferred than ES. But all of this is based on like some very simple theoretical analysis. Yeah, so like that's kind of the gist of it. Like this kind of killed a bit the willingness for anybody to do it. Then you had these paper. So you have this one, fine-tuning language model with just forward pass, and it's like one that was able to scale it, right? Their algorithm is a bit different. It's a bit more complicated. It's called Meso, and then you have like all of these different stuff that it's doing. The accuracy and then the performance that they were able to get was okay, but I think it was lower than like just pure RL. So what they're doing, these guys, is a bit different, and it actually is a bit better. But these one, I think they went to multiple benchmark, right? Well, what we're seeing right now is like there's 2 benchmarks. So that's kind of that. So this is kind of a bit of the literature here, just to ground you, but that's kind of where they're coming from. They're taking back the idea from the past, right? Taking it on LM fine-tuning, not like pre-training any language model, and then they're trying to see if like it actually is working. 2 benchmarks. Okay, wait, we have a few questions. Another unrelated question: does this algorithm basically take a form of moving average across the parameters? Kind of, right? But remember, it's a moving average on the reward type of thing that is happening, right? It's not weighted the stuff in the past actually, so it's not really a moving average, but it's like it's taking the average reward, but then taking that into consideration to decide which parameter perturbation was actually useful. So you can maybe think about it like that in some sense. Yes, I think you could. Asking because the use of combination of moving average can enable the tracking of the evolutional structure within the parameter space. Yeah. So like the method is really simple. Like you can take a look at it. It's not that hard. And then the actual algorithm is actually scaringly simple, but it has some nice property. I'll just show you the gist of the properties over here. And also I'm gonna take the GPU change that they did, because they've done a heck load of it, right? So they're doing a lot of optimization. This is another, I think, important point, is that in most of these, like, that's it, like, theory is nice, but like practice is what matters the most, right? Like if you think about it, like transformer, he has this attention that is n squared, but it doesn't fucking matter that it's n squared, because like it's never the bottleneck anyway, right? So we can just scale these stuff and it's just gonna work. So like even like that, the theory around this, like you can do flash attention v1, v2, v3, v4, whatever. It's good. Like it's better than like all the linearization that you can think of. Versus if you're just stuck on the theory too much, you're gonna kind of not see the actual performance, and then have information to build your theory on, right? So that's that. Wait, we have another unrelated question. I'm simplifying a lot. Okay, this is for Stephen Barnes. Basically, a hypothesis that the brain run model-based RL with the reward function sitting in the hypothalamus and brainstem, and can take basic drive like pain sucks and eat when hungry. Then all higher desire like carrying grow from that foundation. The cortex does the learning, but it's all built on top of these evolved circuit. Yeah, it could be. I don't know. The brain is very complex, right? Like when you dive into it, you're like, what the fuck is this shit? Like, it's crazy complex, man. Like, and like sometimes, you think you got it, right? And actually it's also very plastic. It can change a lot. There is some structure that are, how to say it, like, kind of fundamentally more frozen. So everything that is more in the middle of it is kind of more frozen because it's a bit more ancient. Like the limbic system and all this stuff. But overall, like the brain is really plastic. So, I mean, like, could be, I don't know. And I don't think we can know. So we have to actually do even more research on a computational, on the neuroscience and the computational neuroscience side. There's a lot of stuff to do over there, by the way. Like if you're thinking about, like you really like learning and like the brain, go into neuroscience. There's like an infinite amount of work, right, to be done and research to be done. And it's fucking difficult also because like the brain, just to gather the information from it, like it's not easy at all, right? Like it's not like a mice or whatever that you can just probe to hell, right? Usually like the like a human brain, there's some limitation in what you can do. And even with mice, we don't also understand the whole thing. We understand more about like the lower level animal, like C. elegans, like the worm thing, than the higher level animal, just because the complexity just explodes like crazy. Yeah. So bottom line, Steve Byrne, if you're listening to this, Stephen Byrne, I have no position on your on your thing. I don't know. Cool. So yeah, I wanted to show you this. So this is like what they're claiming, right? That is super cool. So ES only response level reward, making perfect fit for fine tuning on reasoning tasks that have long horizon outcome, which is important right now because right now RL work good, but like if it's too long, it's hard to know what parameters to change. But if you already change the parameters, you literally know because you did it, right? But then you may be going into the problem of like, maybe you should sample more, right? Per parameter change. I mean, that would be one thing that you could do. But if you wiggle a parameter enough, maybe it doesn't matter at all. Like, anyway. So, but like, it's good with this because you have the reward and then you have the parameter wiggling that you're doing. So that's what you have on both sides. So you're not really looking at the action space. It doesn't matter what it does in the middle, right? Does the reward at the end do the stuff that they need to do? Yeah. So more sample efficient than our method that explored in the action page, which is much smaller. So here they find good solution with 30, but then this other guy that I showed you did it with 10,000 population. So every time there's 10,000 dot, right? Like, so this stuff, 10,000 dot, but in our case, it's just 30 dots, right? So more robust than RL across different LLMs. Very interesting. Like literally the LLM doesn't matter because you just like you wiggle the parameters and like whatever happens. Maintain reasonable behavior during fine tuning. Optimize the solution distribution versus just like one solution. It's like good with reward hacking. We're gonna check about it a bit. And like it's not doing that too much. Yeah, and there's no backpropagation that you have to do. There's no gradient at all in this specific setup, right? So it's just like the reward that you have and you're good to go. Yeah. Adi, well, you say the idea behind moving average support Dr. John concept of participatory and knowing, that's why I asked. Okay, cool. Yeah, I didn't know about that. I'll check it out. Thank you. So if we look at the actual GPU friendly algorithm, it's much bigger, right? But it's not that complicated. There's like 1 to 7 element. So we're gonna go through them. The first one is noise retrieval with random seed. You're not keeping like the distribution and you're not like generating it. So like you're just keeping the random seed and this is what you store in the GPU memory, right? So a lot of this stuff is just to save memory. So this is to save GPU memory. You do parallel evaluation. So like you create all of your processes and then like you give them a random seed and then they can just go and do their stuff, right? For each of their the parameter perturbation. You do layer level in place perturbation. So you give the model and then in the process you let the model, let the thing change the model layer by layer, right? So they do to reduce the peak GPU memory usage, the model parameter are perturbed in place layer by layer with corresponding random seed archive. After evaluation of the perturbed model, the model parameter are restored by subtracting the same noise perturbation using the archive random seed. So that's kind of what's going on. There's nothing like everything here is like to save the GPU memory usage. The only additional memory needed is to store a tensor the size of a layer temporarily. You're doing it and then you throw it away, doesn't matter, and then you like do the next step and then you do the next step. Hey Samart, how are you doing? You do a reward normalization. We're already seen it, right? It's doing over here, right? Calculating the z-score for each Rn. So we're doing this Rn with the mean and the standard deviation. This is so that the normalized reward for each iteration have a mean of 0 instead of a deviation of 1. You're doing the greedy decoding over there. You can decomposition of the parameter update. So at the end of each iteration, the aggregate update of the model parameters is performed in place again in a decomposed manner, gradually adding up layer by layer and seed by seed, significantly reducing the peak GPU memory needed, again, for GPU memory saving. And then they're just the learning rate. So like this is the actual formula, right? But they're just taking these two and then they're just like making one learning rate. So the learning rate in there is very small because of that, because like they're digesting it into that. Yeah, that's kind of what the stuff is. And this is reflected here, right? So you have the same overall process here for like the for loop, right? And then you have like the random seed that you're taking for each of them. So you're creating the seed so that you can repeat the stuff. So in the first for loop over here, you're doing your group stuff, right? So you're gonna spawn each of the process and do that. So for process handling, we set its random number generator using a random seed, blah, blah. And then for each LLM layer, you're gonna go layer by layer, you're gonna do that. You're gonna compute the reward, and you're gonna do it again, right? At the end over here. And then here at the end, when you're out of here, you should have all of your reward score. You're gonna normalize all of them. And from here to here, you're gonna reset the current number random number generator. You're gonna do for each LM layer, you're gonna sample the noise and do it again with like the normalized stuff now. And that is what you're gonna update the model parameter with, right? So here you normalized it and then you're gonna compute it. So you're trading off, right? If you look at this implementation, this is not memory friendly at all, right? Because there's a lot of bulky stuff that you're doing. The other one is more memory friendly, but it's not compute friendly. There's more compute going, there's more for loop and stuff. But it doesn't matter because the GPU is good with that. So fine tuning, kind of memory constraint. So we're doing all this gymnastic to do that. So any question here, you can go step by step on it, right? But like the only difference between the two is that we're trying to save memory here. Okay, perfect. So if we look at the actual two results, right? One we already saw, it's pretty much just this, right? Just there's not much to say. It just works, right? Like this is it. Like it works. And then the second one is interesting. Second one is a conciseness type of task, right? And if you was it Dwarkesh? I think yes. I think wait a second. I'm gonna pull up his tweet. Wait, it's Dwarkesh. My man is doing he's doing RL. So he went on and then he was doing he's the host of the podcast stuff. He wanted to get a better intuition of our work and whatever it is, and then like he was doing teach channel chat to a 5-digit number, a bit like our stuff, right? And what happened is that the reward function got hacked in the sense that like the model generation realized that he had just learned a way to call the built-in Python interpreter, right? So it's not actually adding these numbers, just like using the model, like the Python interpreter. So it just give it that, and then like it get the answer back, and then that's it. So this is kind of an example of reward hacking, right? So RL is prone to this. It will go and then it will hack the reward, and then like you get something that hasn't truly learned, right? What you wanted to learn. It can get worse than this. So in this case, like conciseness, if the reward function is just conciseness and you're not looking for accuracy, you're just gonna get spaces or nothing, right? Just hey, super concise, I didn't do anything. And like you have to be very careful of how you craft the reward, which is a pain, right? In this specific case, it's a bit less prone to that, which is interesting. So we have Brock that asks, do you stream every week? I try to, right? I try to stream every week. And mostly going to like papers like this, or sometimes we actually code some algorithm for deep learning. It's kind of what I do. And create a space for you guys to ask all your questions. By the way, Thursday we're gonna stream again, right? With our guy Yulu from this paper. We're gonna ask him a whole bunch of evolutionary strategy questions. Cool. So this is the conciseness thing. So this is let's say the prompt is this: solve 3 plus 5, right? And the verifiable solution is 8, right? If all bird can fly and penguin are bird, can penguin fly? The answer is no, right? Like it don't matter what you're saying more than that. So that's what we want the model to be able to do. At the end, we want to have it like have the smallest kind of answer all the time, right? And that's another whole bunch of them for the evaluations, right? So if we look at the performance, this is for the conciseness reward, and then we also take a look at like how it diverge with respect to the base model, right? And what we see here is that like these are the hyperparameters, right? Doesn't matter too much, but like for Quen, for these two versions of Quen, right? With these parameters, it actually is doing reward hacking here, right? It says here, the star label indicate case where reward hacking was observed. So these two models are like, it's the same 7B model all across, right? But with these set of parameters, unfortunately, the model is learning to do reward hacking. In these set of parameters, it doesn't. So this is good, right? But it shows that for RL, you really have to make sure that your parameter space is properly swept. Well, yes, get good result here, right? And robust also across run, right? So there's very low standard deviation here. Versus them, they're like an order of magnitude greater than that. And the KL divergence is pretty small, so that like it's really close to the base model, which is something you want, right? You don't want it to kind of start diverging, because you're gonna like make it do better in conciseness, but then you will forget to do basic math and stuff like that, right? Or like to, I don't know, like say hi and like be polite, right? If the parameter space changes too much, which is what KL divergence is, right? KL divergence, you have two distribution like this, and it's like the degrees at which like these distribution are changing, right? So if it's changed a lot, it means that there's a lot of parameters that have changed. But in this case, it's the smallest one. So there's the smallest amount of KL divergence. And if you look at the Pareto front here, right, you see this blue line is ES, right? These ones are actually like these lozenges. I don't know how to say it, right? This is the ES, and then the GRPO is the other one. It's like this line, right? And what you see is that it needs to diverge a lot for GRPO in order to get the best result on this conciseness reward. It has to, otherwise it doesn't work that much, right? It gets stuck here. Versus this one, it doesn't have to diverge a lot in order to get a good performance. And even there, like you can stop technically here, you barely change anything, right? You barely change the parameter space and still you get like the proper reward. So that means, theoretically, that like they should, I would say they should have run a whole bunch of other benchmark. Maybe they don't have the compute to do that. But you're able to see that like the model stay roughly as like the good performance of before, but now it also have this new like functionality that it has because of your fine tuning. So you keep the generalizability while like being very close to whatever you're trying to do. But that's it. So this is what they're doing. Like I think they use KL divergence here versus like a whole sweep of benchmark because literally they couldn't have the compute to just run them at all, right? But the idea here is that it's not doing reward hacking and it's not changing the parameter space too much. It's actually finding like the right set of parameter to change, all by just wiggling this stuff a bit, right? So that's the idea. Do I have other stuff to show you on the paper per se? So this one we got to, yeah, here you see, applying evolutionary algorithm to optimize billion of parameter in LLM is generally perceived as to be intractable. A lot of people in the comments have been saying that under my Twitter post. But like, theoretically, yes. But in the implementation, it actually can work, which is funny. He might, like the author might have killed some good thing that is a bit simpler than RL. And then what else here? I'd say so that thing RL method turned out to be sensitive to hyperparameter. And yes, remember, like it's only there's one set of parameter that is the same across LLM across the whole runs, which is crazy, man. Like it's just like one. You don't have to do hyperparameter sweep for their stuff. Kind of wild, and it's more simple, efficient. So the show, like there's a figure at the end, show the learning curve to reach the same level of fine-tuning performance as RL. We need less than 20% of the training sample evaluation in most cases. So actually, we're gonna actually go at it. It's figure 6. This is figure 3, 4, 5, 6 here. Right. So training curve of ES and RL, and then the number of sample evaluation. And ES, like, it's like way above all of it. And like, you don't need that much sample in order to get whatever you like better performance than the other one, right? Which goes against like everything. Like this part, I'm not like this part. Honestly, I'm like, we're gonna have to have this reproduced over many other benchmark, because if this is true and it's more simple, efficient, it seems to just be much better, right? And if it's true that it's much better, think we should like actually use that instead of RL, right? RL is a bit of a mess. Like it's always difficult to work with. And if it worked well with LLMs, like why not? Like this should be, it's scalable. It's fucking simple. You look at their algorithm, guys. You're just like wiggling the board a bit. We should do that. Right? I think definitely like this is something we should be doing much more, right? And look at this curve, right? Look at this one. Look at this. Like with a few sample here, right? Minimal amount. Yeah, you directly have 10% improvement. Straight up. For me, it's crazy. Like this part is a bit crazy. It's like the smallest model possible. RL can't do anything, but this one can. Yeah, it almost look like it doesn't make sense, right? So yeah, that's kind of that for this part. There's a whole bunch of other experiment in the appendix, but like it's more of overview, an overview of like a deeper dive of the methodology per se. But that's it. And the other thing also that is interesting is they're using vanilla ES. So in the ILIA paper, they did a whole bunch of things, right, in order to make it even more performant for robotic kind of tasks. But in this case, they're not doing any of this. They're just using like the vanilla thing, barely any parameter sweeps. They wanted to show that like, yeah, this thing is much better on its vanilla form, and we should maybe take a look at this more. Yeah. And one thing that they're saying, an interesting future direction is to analyze how such small population is possible, because they're just using 30. In other paper, they're using 10,000, and this is just like good. And they're saying something interesting. They're saying this is related to the observed low intrinsic dimensionality of LLM. So there's maybe a good synergy between ES and LM because of like the shape of its parameter space. Yeah. So that's that. It's pretty cool. Yeah, they have a good discussion in here. You can read about it. But overall, great paper. But I would like to see more, right? Overall, I would like to see a bit more of a deeper dive into what's going on. Hi, Krush. Glad to have you here. Hello, Avi. Nice to see you, boss. Yeah, it's too good to be true, honestly. Like, there's no drawback. Like, you can read it for yourself and you can run the code. There is literally no drawback. I was waiting for them to say like, but you know, it actually sucks because this, that. There's none of it. Like, it's not doing reward hacking. It's more sample efficient. We get better performance, order of magnitude better performance, right? We didn't even fine tune the parameters, right? Like, what else do you have? Like, the algorithm is more simple, right? It's like there's no second model. There's no like complicated reward function you have to do. By the way, on the conciseness, they're just like fine tuning on the conciseness, not even on the correctness. It's fucking wild. It's working, right? I mean, like, it's so good that I like I'm in my head I was like, they're gonna retract this and they're gonna find that they fucked everything up, right? But so far no, it seems to be good. I don't know why we're not talking more about the evolution strategy, if like especially for LLM, if it has this impact. Maybe like people are just not interested that much. For me personally, I was not that interested that much about that because it was like another genetic algorithm type of stuff, right? But it's not even genetic algorithm. It's just like wiggling the parameters a bit. Like, yes, there's the different population, but you're just using the reward to have a direction and then you go there. There's nothing like, oh, there's this population and then you're gonna mutate these things and then you're gonna cross over that stuff and then this gonna yield off. None of this Darwinist type thing, right? It's just literally there's a whole bunch of parameters in the model. We're gonna wiggle the billion of them and then we're gonna get something out of it. And then we're gonna like check the reward of it. And then all of these 30 reward will tell us which direction we should go. And we're gonna go there. And you know what? We're gonna do it again and again. That's all there is, man. Like, it's crazy. They're not even doing like multiple sample per parameters, which is honestly that could work also better. Like, if you have multiple sample, it can get even better reward per element. Are they doing this? I don't think they're doing it at all. No. It's wild, man. What the fuck? There's just so much that you can technically take that, right? And if you have access to more compute, crank this up, right? Like, you can do like by the way, like, if you're interested in doing research here, like, this is a good paper for that. The code is simple, right? You don't need massive amount of compute to run this, and you can do very targeted experiment here and get some good. For instance, you can just like add another benchmark. You just add another benchmark in there and you test it on it. You test like GRPO, 830, PPO, and then like this ES. You don't change anything else, right? run it and like take a look at it if like it has good performance. Anyway, so this is the paper, right? We're gonna actually talk to oh yeah, that's the last thing I wanted to show. We managed to get, look at this thing that I did, right? Boom, right? We're gonna talk to Yulu. So Yulu Gan, such a cool name, man. Like, look at every little ingredient is there for this to be like the breakthrough of like 2025, right? The guy is smart. He like wrote this shit. MIT dude. Super simple method. It just fucking work, right? And he has a great name. What else do you want, right? So we're gonna talk to him on Thursday, October 23. I was able to broker that. Thank you, Lulu, if you're watching this. You can check out his Twitter, right? Very smart dude. And if you have any question, right, don't hesitate to like send it to me, and I'm gonna try to do like a nice interactive interview on Thursday around 10 to 12. Yeah, that's it. Next day, 17 new paper on archive. Adiwal say it's super dope. Yeah, actually it is super dope. Yeah, it's pretty cool. So if should you read this paper or should you not? I think you should. Yeah, I think it's a good paper, at least to give you some perspective and to show you something that happened quite a lot right now. It's like there's a lot of ideas from the past now this year. I don't know why 2025. That idea from the past that are getting reached back and then re-implemented with LLM, and it just works, right? So like it's good also for you to not just look at the latest kind of same direction that we're going again and again, but also to kind of look at a different direction and a different ideas. Diffusion is one of these ideas that was brought back to like the current days and just now work. Wow, did we get like nice properties? Like a reasoning also, like with the TRM that we saw last time. Like it's an old idea that like we're using now, and it's working super well, right? So like it's good for you to get these ideas and like at least know about them so that you can try a different angle, understand like what actually is at stake in terms of learning in general. And that's it. Any question, folks, before we cut the stream? It was a fun one. So, fantastic. I wish you all a great rest of the week, right? See you on Thursday, if you can make it. Otherwise, we're going to just record it. And yeah, have a great day. See ya. Yeah, somebody said like Lacan GovNet basically just combined backprop with like Fukushima's architecture. That's what's happening, right? Every bottleneck that we popped in deep learning was that. It was like a combination of like the current ideas with the old ass ideas in the past that we just repurposed and now it works best. Yeah. Cool.